Welcome back to the channel. Today we are tackling a real-world municipal challenge right here in Toronto. How to marine road distress and pothole detection using computer vision. If you ever wonder how city can track infrastructure work faster, this project is the answer. We built an end-to-end pipeline using a Samsung Galaxy mobile model to capture 104 street-level photos guided by official 311 municipal data. From there, we developed custom Python tooling to draw precise polygon masks, created standardized YOLO annotation, and training YOLO 11 instance segmentation model locally on an NVIDIA GPU using unstructured Excel metadata. By the end of this video, you will see how we achieved an impressive accuracy 0.7, automatically classifying specific pothole categories, subcategories, and repair urgency levels and unseen at-fault image. Let's dive into the development. When building a robust computer vision model, data quality is everything. For this project, the images were captured manually using a Samsung Galaxy S25 Ultra during optimal lighting conditions, especially targeting the road distress feature reported by 311. However, raw street photography contains a lot of background noise, like passing cars, pedestrians, and surrounding buildings. That can easily confuse a machine learning model. To fix this, every single image was carefully cropped to isolate the anomaly. Even though this resulted in varying dimension and different resolution across the dataset. Removing those distracting background elements ensures that the YOLO 11 model focuses entirely on learning the precise pattern of the road distress rather than noise. Now, to train a high accuracy instance segmentation model, we need precise polygon masks around our potholes. Signs of the shelf tools didn't always fit our exact criteria. I wrote a custom interactive annotation script right inside Jupyter Notebook using Matplotlib and OpenCV. Let me show you how it works under the hood. We load our image and read its height, width, and channel using OpenCV, setting up a Matplotlib canvas with a Matplotlib widget to make the plot interactive. Next, we define an on-click mouse event handler. Every time you click on the image, the script captures the exact X and Y coordinates, appends them to a list, and plots a red dot. As you keep clicking, it draws a blue line connecting the points in real time, letting you trace the exact contour of the pothole boundary right on your screen. Finally, we use IPython widget to create a clean, green, safe polyline mask button. When clicked, the script creates a blank black canvas matching the original image dimension, maps or clicked points into an OpenCV array, and draw a white polyline mask over it. It then automatically exports that mask as a PNG, disconnected the event listener, and close the plot to the kit memory clean. This custom setup gives us total precision over our training labels without needing heavy third-party labeling software. Now that we have our custom polygon masks saved as PNG files, the next critical step is converting them into standardized text labels that the YOLO 11 segmentation model can understand. Let's look at the script that automates this bad conversion. First, we set up our directory pointing to our input folder containing the same mask and our output folder where the YOLO training labels will live. The script loops through each mask image, loads it in grayscale, and applies a binary threshold to ensure a clean black and white separation. Next, we use OpenCV find contour function with change approx known. This is important because instead of approximating or simplifying shapes into a few corners, it captures every single point along our hand-drawn contour. Because hand-drawn lines can sometimes contain redundant points or a small artifact, we added two smart fixes. First, perimeter filtering. We check R length to filter out tiny noise dots, making sure we only process actual pothole outlines. Second, smart downsampling. If a contour has more than 100 points, we use NumPy line space to evenly downsample it to exactly 100 points. This keeps our training file clean and lightweight without losing the shape of the pothole. Finally, notice how we normalize the coordinates by dividing the x value by the image width and the y values by the image height. YOLO requires normalized floating points coordinates between 0 and 1. The script then writes everything off of the X files, starting with our class index 0 for the pothole, followed by all coordinates formatted to the 6th decimal place. Once these text files are generated and placed into our training level directory, we are fully locked and loaded for model training. Before we can actually train our YOLO 11 model locally, we need to make sure our Python environment is fully optimized to harness the power of our graphic card. Running a computer vision model on a GPU is significantly faster than using a CPU, so getting the right libraries installed is a crucial step. Let's walk through the setup snippet. First, cleaning the slate. First, we make sure there are no conflicting CPU-only versions of PyTorch lurking in our environment by uninstalling Torch, Torch Vision, and Torch Audio. We also clear pip cache to prevent it from accidentally pulling cache CPU builds. Second, forcing CUDA installation. Next, we install the dedicated CUDA 12.4 version directly from PyTorch well repository using the index UR flag. This links PyTorch directly to our NVIDIA GPU drivers. Third, hardware verification. Finally, we run a quick verification check using Torch CUDA is available and print out the device name. When you run this block and see your specified GPU model pop up in the output console, you know your local hardware is fully unlocked and you are ready to kick off high-speed model training. We have our image cropped, our custom polygon mask converted into normalized text labels, and our CUDA environment verified. Now comes the exciting part, configuring and training our YOLO 11 instant segmentation model. Let's look at how everything ties together in Python. First, before writing any code, we need to make sure our directory structure is organized exactly the way YOLO expects. We have an image folder containing our train and val, subfolders, and parallel label folder containing our train text annotation. All of these paths are mapped out inside our config.jl file so the model knows where to look. Now walking through the training script. First, loading the model. We initialize YOLO loading the lightweight YOLO 11 segmentation backbone. Second, the training arguments, model train. The parameter data is equal to config path, point to our YAML configuration file, linking our dataset path and classes. The parameter epoch equal 50. We run training for 50 epoch give the model enough iteration to learn the intricate feature to road distress. The parameter EMJS equal 6 and 400 standardized or input image size to 640 pixels. Even though our raw photos have varying resolution and dimension, YOLO automatically handles the resizing and padding. The parameter device equals 0 explicitly tells the model to run on our dedicated local GPU, like an RTX 3070, ensuring lightning fast tensor operation. The parameters workers equals 0, a crucial fix for Windows user. Setting this to 0 disable multi-thread data loading, preventing common multiprocessing data time-ups on Windows. The parameter batch equals 4. Set a safe lightweight batch size to fit comfortably within our GPU VRAM. The parameter plots equal true. Automatically generates validation plots, confusion matrix, and loss curve so we can evaluate our model performance post-training. Once you execute this block, you will see your GPU spring to life and the model will start learning how to automatically segment and classify photos. Once training is complete, the next critical step is evaluating how well our YOLO 11 model actually performed on unseen data using the validation set. Let's look at how we run the validation script. We call model.val, and just like during training, we pass worker equals 0 to prevent any Windows multiprocessing data timeouts, and batch equals 4 to keep our GPU memory usage light and stable during evaluation. After running this, the script pulls the key segmentation performance metrics and prints them out. First, metrics.seg.map give off the overall mass, which measures the precision across multiple strict EO thresholds, and metrics.seg.map50 give off mass, which is our standard accuracy benchmark at the 50% intersection over union threshold, where our model hit that stellar 0.87 score. Running this validation gives us concrete, quantitative proof that our custom dataset and local GPU training pipeline successfully built a highly accurate road distress segmentation model. We have our image, our custom mask, and our training environment ready. But to make this true multi-class instance segmentation model, our YOLO architecture needs to know what specific type of road distress it is looking at and how urgent the repair is. To manage this, we compile a structured metadata Excel sheet that categorizes each pothole using precise industry standard definition. First, categories like crack, crocodile, patching, and pothole. Subcategories, which break down a specific field condition like crosswalk, isolate pothole, water ponding, severe path failure, and loose aggregate. Urgency tiers, rated as high, medium, or low. Now let's look at how the Python code translates this Excel sheet directly into our YOLO configuration file. First, loading and deduplicating. We use pandas to load our Excel sheet and extract unit combination of category, subcategory, and urgency using drop duplicates. This ensures every unit combination gets its own dedicated class ID. Second, building and YAML structure. We set up root path for all training and validation image directories. Third, generating compound class names. We loop through each unit combination, cleaning up space and slash to default clean, matching readable string identifiers. Each one is assigned an index number starting from 0. Exporting the config. Finally, the script writes everything out into config YAML. This automated script is a massive time saver. It dynamically links our field metadata straight into YOLO, letting our model classify both the exact nature of the repair urgency of every pothole is detected. Important. Now that our model is trained, how do we actually get our custom categories, subcategories, and urgency levels back out of it? Remember, a computer vision model like YOLO doesn't think in words of reason like language model. When it looks at an image, it simply outputs a number of class ID. To solve this, we use a neat trick during training. We join our category, subcategory, and urgency into a single compound label using double underscore. So, in this script, we run our prediction on a test image. The model gives us back a class index, for example 0. Our Python code grabs that label string, split it at the delimiters, and instantly translate the raw numbers back into readable details like category, subcategory, and urgency, so we can print it neatly to the console, specifically in this part of the prediction. We should have approximately 1000 images in the training to integrate a block into the model that recognizes the category in the image. We have trained our model, validated its accuracy, and mapped out all our metadata classes. Now comes the moment of truth, running inference on a brand new image to see our model segment, the pothole, and output its exact classification and repair urgency. Let's walk through the final prediction script. First, loading training weights. We load our fleshly training model by pointing directly to our saved weights file. Second, running prediction. We pass a validation image like 101, set our confidence threshold like confidence equal 10%, and enable save equal true. So YOLO automatically saves the visual annotated result with the segmentation mask drawn right over the pothole. Third, parsing compound labels. Because our class names were formatted earlier as compound string, the script loops through the text boxes, grabs the class ID, and split the string back apart. It cleans up underscore and replaces them with readable spaces. 4. Structure output. Finally, it prints out a clean analysis report in the console, showing the detection confidence, the exact ROAC distress category, the specific subcategory, and whether the repair urgency is high, medium, or low. And there you have it, from a smartphone photo taken on the street of Toronto to custom polygon masks, local GPU training, and automated civic triage, to have built a complete end-to-end computer vision pipeline for a municipal road maintenance.